First, the introduction. This video is about the process to find out the maximum and minimum value, that is called optimization. Many application problems in calculus involve function to find maximum and minimum value. We have three objectives for this video. First, to develop the ability to solve real-world optimization problem using mathematical principle. Second, to calculate the highest and lowest point of a curve in a graph or to know its turning points. And third, to develop logical reasoning and critical thinking skills to formulate and interpret mathematical models. Why do we need to learn application of differentiation? So we have three goals here. First, to understand more about application of differentiation. Second, to increase our understanding of applied maximum and minimum. And third, to be able to solve the question with a suitable formula.
Let's start with the second question we solved. The question is, a manufacturer wants to design an open box that has a square base and a surface area of 180 cm square. Now, let's walk through the solution step by step. To solve question A, we need to determine the dimensions of an open box with a square base and a fixed surface area, such that its volume is maximized. The surface area of the box includes the square base and the four rectangular vertical sides. Using this information, we set up an equation for the surface area as the sum of the area of the square base and the total area of the four sides. From this equation, we express the height of the box in terms of the side length of the square base. Next, the volume of the box is expressed as the product of the area of the square base and the height. Substituting this expression for the height into the volume formula gives us a single equation for volume as a function of the base side length. To maximize the volume, we take the derivative of the volume function with respect to the base side length and set it equal to 0. Solving this equation gives the critical point, which corresponds to the side length of the square base that maximizes the volume. To confirm this is maximum, we check the second derivative of the volume function. Since the second derivative is negative, it confirms that the critical points give the maximum volume. After finding the side length of the square base, the height of the determined by substituting this value into the equation derived from the surface area. These calculations provide the dimensions of the box, the side length of the square base, and the height. For question B, we calculate the maximum volume of the box using the dimensions found in the question A. The volume is expressed as the product of the area of the square base and the height. Substituting the side length of the square base and the height into this formula gives the maximum volume of the box.
Now we move to the next question. Figure shows a piece of wire length 130 cm is bent into the shape A, B, C, D, E, F, G, given that BC equal to DE, which is this part equal to this part. And if we look truly to the shape, BC and DE is equal to AG, which is 4y. And 4y divided by 2 will get 2y of each part. So this part will equal to 2y, this part will equal to 2y. Okay, now question 1. Express x in terms of y. So the question wants the answer in x equal to y. So now we take a look at all the information given in the question. It says that 130 cm is bent into the shape A, B, C, D, E, F, G. So what is 130 cm? 130 cm is a perimeter. Why it is a perimeter? Because 130 cm is bent into the shape A, B, C, D, E, F, G, which is all of this bent together, and it will equal to 130 cm. Now, we all know that all of this part will equal to 130 cm. So we can make the equation by using the parameter. Okay, so 4y plus x plus 5, this part is equal to this part, plus x plus 5 plus x plus 2y plus 2y equal to 130. Okay, now if we simplify this equation, it will be 8y plus 4x plus 10 equal to 130. Now, the question want the answer in the term of x equal to y. Now, we move all the number that doesn't have x to the right. So, 130 minus 10, it will be 120 minus 8y for x. 130, 20, divide by 4. And the answer, it would be 30 minus 2y. So, this is the final answer. Now, we move to the question number 2. Show that the area enclosed by the wire A equal to 200 minus 12 square. Okay, this is mean we have two rectangle. Okay, A equal to 200y minus 12 square, y square is mean the area sum of this between two rectangle. So, area rectangle 1, 4y multiplied with x plus 5 plus rectangle area of the rectangle 2, which is 2y multiplied with x. Open the bracket, we will get 4xy plus 20y plus 2xy. We simplify the equation, we will get 6xy plus 20y. And if we look through the equation given, it doesn't have x, but in our question we have x here. So we need to use this answer at above question to substitute into this equation. So the equation 6, substitute this answer 30 minus 2y, 6y plus 20y. We simplify the equation and we will get 180 plus 20, we will get 200y plus 12y square. And this will equal to this equation, and this is the final answer. Okay, last question. Hence, find the maximum area of the shape ABCDEFG. So the question one, the maximum area of the shape ABCDEFG. To find area, we use this equation, A equal to 200y minus 12 square. The answer of the above question. Okay. To define the area, we have to differentiate the equation. So, differentiate dA over dy. Differentiate 200, we will get 200y, we will get 200 minus 24y. Now, let dA dy equal to 0. 24y equal to 0. Now, we rearrange the equation and we will get 25 over 3. Okay, and now, to find the maximum area, we have to differentiate once again, and d square a over dy square. 25 over 3. We will get negative 24. If the answer we get is in negative, it will be a maximum area. And if we get the answer in a positive, it will be minimum area. And now the answer that we get is a negative. So it is a maximum area.
In conclusion, identifying the right formula and accomplishing both first and second derivative correctly will lead to solid answer, a maximum or minimum cost.